Let's talk about non-homogeneous equations. So what do I mean by non-homogeneous? Maybe just look at a quick example here. Here's an example of a one-dimensional non-homogeneous heat equation. And non-homogeneous relates to these terms here, to the gamma in the equation and to the a's and b's in the boundary conditions. So we call them the non-homogeneities. And an easy way to remember homogeneous versus non-homogeneous is you test if 0 is a solution. Okay? So if you don't have the gamma there, then you can sub in u is 0 and everything is just fine. But if gamma is there, then 0 is not a solution. Same for the boundary. If a and b were 0, then you could sub in u is 0 and everything is fine. However, now they are not. So we need to find methods to deal with these non-homogeneities in the equations. The general idea is right here. The first, we try to find an ODE which takes care of the non-homogeneities, so that then we can define a homogeneous PDE for the rest. And we know how to solve homogeneous PDEs because we use separation. Alright, this sounds rather abstract, so let me do this for this example here, example 3. Here I indicate what would happen if you use separation directly. So if you use separation directly, which is nothing wrong with that, you have the first idea, you do this. So you sub it in, right, for the time derivative you get a t prime, for the spatial derivative you get an x double prime, the gamma term though remains. And then you try to shuffle it to one side or the other, so that one side only depends on t, and the other side only depends on x. But then what happens is, for the gamma term, you get something which depends on t and on x. Right? So in the denominator you have x of x and t of t. So it's both there. And that's where the method fails. So there you cannot say this is equal minus lambda because they are not separated. Okay, so the direct separation does not work. So we have to do something else. And the something else is right here. We write the solution u of xt as a sum, v of x plus w of xt, where now the v, this here, should take care of the non-homogeneities. I hope I can find a simple, let's say, ODE for v, which I can solve, and then the homogeneities are taken care of. And so then this dude here will solve a homogeneous PDE. Now this sounds a bit crazy, but remember, we had the superposition principle. It allows us to take sums of solutions. So maybe we can indeed do this. Write u as a sum of v plus w and solve the whole shebang. Let's take this idea u is v plus w and sub it into the PDE. Remember we had a time derivative. So ut would then be, well, v does not depend on time, but w does. So this would just be the partial derivative of w with respect to t. If we do the spatial x derivative, we get uxx, which then is equal to v double prime, this does not depend on x, plus wxx. And you notice the notation. For v, I use a prime because v only depends on space and nothing else. So there's no need to write a partial derivative. For w though, we have x and t dependence, so I write wxx. Okay, so then this has gone here. So this has gone here. And so then, and in addition the gamma. So then this is our new version of our PDE. Now I said v should take care of the non-homogeneity. So why don't I just say v makes this equal to 0, which I did right here. So I want to choose v so that v double prime plus gamma is 0. Oh, that would be so cool, because if I can do this, then what do I keep for w? Well, for w I keep wt is wxx, which is now homogeneous. Let's look at the boundary conditions. U at 0 is then v at 0 plus w at 0. And this, of course, is a. U at 1 is v at 1 plus w at 1, which is b. So these were the boundary conditions, the non-homogeneous boundary conditions. And again, how if I can say v0 is a, maybe? And v at 1 is b, yoo-hoo! Because then w at 0t would be 0. And w at 1t would be 0. Provided we can do all this. So far it's just an idea, so we still have to do the calculation. But let me summarize what we did. So our wish list is here. The wish list is that v satisfies v double prime plus gamma is 0. On the left boundary it is equal to a, on the right boundary it's equal to b. And if we can make this happen, then we need to worry about the initial condition. So we said time is 0. U at time 0 is again v plus w at time 0. And u at 0 had been set to be equal to 0. So then we can solve this for w at 0 is minus v. So if we can get v from our wish list, we can sub it here, and then we have the initial condition for w. All right. So then let's collect what we have for w. So we get a homogeneous PDE. We get homogeneous boundary conditions. And then we get an initial condition, where the v appears, which was from the earlier problem for the v equation. Let's start with the v problem, right? We have v double prime is minus gamma. So we integrate it once, we get v prime is minus gamma x plus a constant. Let's call this little a. So then v is minus gamma over 2 x squared plus ax plus b. And then we can sub in the boundary conditions. So we have v at 0 is a. And subbing it in there, this is also the little b. And v at 1 is a big B. And subbing all this in, this is minus gamma over 2 times 1 plus a times 1 plus little b. And little b is big A. So then we get little a to be equal to b plus gamma half minus a. Alright, and so then we can plug in the little b here and the little a there. We get a quadratic function for v. V is minus gamma half x squared plus the a coefficient x plus the b coefficient. So then here we have our solution v of x. Now this takes care of the non-homogeneity gamma and also of the boundary conditions a and b. And this means now for the w we can happily apply our separation of variables. W is x times t. We are separating the derivatives. You have seen these steps a few times before, so now I really shortcut. And we get a homogeneous spatial problem here. X double prime plus lambda x is 0, x at 0 is 0, x at 1 is 0. And we get a time problem there. T prime plus lambda t is 0. And lambda is a separation constant. Right here. Now, the term on the left, the spatial problem with homogeneous Dirichlet boundary conditions, we have solved now many times, at least twice. So I'm not going to go through the cases lambda positive, lambda equals 0, lambda negative again. I just know what it is. And so I just cite. From earlier calculations, we know the eigenvalues are n squared pi squared. The eigenfunctions are sine functions with the index n pi. So then we can take the lambdas and put them in here. Then the t problem will just have an exponential solution, so then the tn is e to the minus n squared pi squared t. This goes quick. Remember, in earlier videos I needed, I don't know, 2-3 pages to do all this. But now we did this so many times, I use it. And if you do homework problems, you can just use what you know. Perfectly fine. So then Wn is a product of x and t. T was given up there. Xn was given up there. Wonderful. And then we can use superposition to write w of x and t to be the sum of all those. So n is 1 to infinity. Some coefficients an. E to the minus n squared pi squared t sine of n pi x. Cool. And then remember the last step was to use the initial conditions. And the initial conditions were given at time is 0, w equals minus v, and minus v is a parabola from above. So here I wrote down the solution again with coefficients bn. I think earlier I called them an. Doesn't matter. If you set t is equal to 0, then you get the initial condition. So let's do that next. Right, so we set t is 0, so the exponential term drops, and we get a Fourier sine series for a v. Okay, actually for minus v. Minus v is then a Fourier sine series. But that's all right. I know how to do Fourier sine series. So I use, for the coefficients bn, I use the formula for the Fourier sine series coefficients. So we sub in the v function, and this was the quadratic polynomial here, with the minus gamma half x squared plus a half gamma minus a plus bx plus a. And now we have to integrate this out. And again, I'm using a shortcut, because again, we have done Fourier coefficients of sine many, many times over. And I can use results which we have done before. What you have to do though, you have to multiply each individual term, this one and this one and this one and this one, with the sine, and integrate all of them separately using integration by parts. For the last one, for example, for the a times sine, you can just integrate and you get minus cosine, so that's easy. But then if you have the x here, x times sine of n pi x, you have to do integration by parts once. And we did this before. For the x squared term though, x squared times sine of n pi x, you have to integration by parts twice. Allow me to be fast here, and this is the result you get. Okay, so then these are the coefficients bn, and now we can put everything together. So you remember the original u is v plus w. V took care of the non-homogeneities. W is a homogeneous solution. And let's sub it all in. So then v was this guy here, the quadratic polynomial. And the w had these coefficients bn for their sine series representation. All right. Here's one more little detail. What happens if t goes to infinity? If t goes to infinity, then this guy goes to 0. So all the exponential terms, e to the minus something t, is always goes to 0. So meaning the whole series stuff goes to 0. This guy here goes to 0. And only v remains. In the limit as t goes to infinity, the solution u approximates the equilibrium solution v. So in this context, v is then also called the equilibrium solution or the steady state solution, like we have discussed before. And this part which goes to 0, this w part, is called the transient solution or the transient part. Isn't that cool? So we started with v just to help us for the non-homogeneities, but it turns out actually it has a very good meaning. It is the long time limit of the solution. So let me show this to you in a numerical simulation here. So the v is plotted here. It is an upside down parabola. We take an initial condition, something wiggly. Right, so now we are increasing time. 0.01, 0.02, 0.4, 0.8, 0.1, 2, 4, 6. Oh yeah. And then we are very close to the function v of x, as we were expecting. And you see the convergence is rather quick. Time is not even 1 unit.